The last thing that we're going to do in Unit 1 is explore graphing. So, graphing is a really excellent way of showing the relationship between two variables or between two parts of a lab. Okay. The way that we graph is that we want to make sure the graph tells you the whole picture. In other words, you need a title. Your title should clearly state the purpose of the graph and include your independent and dependent variables and be specific, including units. Now, if you're not too sure what that means, the independent and the dependent variables are your axes. So your axes will be labeled with the variable and the unit, and your independent variable is your x-axis. In other words, I think of this as your control. Okay, independent is the one that you control. So in a lab, it's the one that you're changing, whether this be changing mass, whether this be changing velocity, right? And then your dependent variable is your vertical axis, and this is your result. When you change your mass, how much more does your wooden beam move? The movement of the beam is dependent on the amount of mass that you hung. So dependent depends on the independent. So this is always your dependent and it depends on your independent. Okay. Then when you have your title for your graph and you've labeled your axes, including what they are and what units they're measured in, you want to make sure that you've chosen your scale carefully. Now, if you're letting a computer do this, it will do it for you, but you want to make your graph as large as possible. In other words, you want to use as much of the axis as you can. Then when you're plotting your data, you'll just put it in with dark dots, and then your dots won't always connect. What we're going to be looking for is what we call linear relationship between our data. So we're going to be looking for lines. You're not responsible for connecting the dots. You're looking to see if the relationship goes up in a linear fashion. In other words, when one variable increases, the other one increases at the same rate. Okay, so I've got 3 examples of graphs below here. One of them is excellent. 2 of them are awful. So first off, let's pick out the excellent graph. Okay, which of these 3 do you think ticks off all the boxes before? So it has a title. It has my axes labeled. It has an appropriate scale. It has dark dots for your points. It doesn't connect the points. In other words, has a line of best fit instead. Well, this one. This one's awesome. Okay, this shows what we're graphing. It's the effect of, and I love starting graph titles with this, the effect of increased automobile speed on the average ticket cost. So it's showing that the average ticket cost depends on your speed. Okay, so title's great. Our axes are labeled with units. Our scale is consistent, right? A scale of 10, a scale of 40. We have our dark dots, and it's a basic linear relationship. So I can see that if I drew a line of best fit, which should go through 0, 0, in ours it always will, because if you don't speed, you don't get a ticket. And then you can see this linear relationship between the 2 things. So this is an awesome graph. So what's wrong with these 2? Well, lots. This one, no title. And no title on these axes as well. The other thing is you'll notice that there's no consistency, right? This is a scale of 10. This is 13, and then it goes 16 and so on. So it's not a consistent scale on either axes. But they did that so that they could join their dots, right? So they plotted points in a linear fashion so that it came out linear. So the linear part looks great, but it's fake. This graph, what don't we like? Well, number 1, don't connect the dots. Don't connect. We are looking for a line of best fit. Sorry, that's the first thing that drew my eye. First thing we should look at is the title. How much does a speeding ticket cost? Huh? Okay, well, I could assume that this is cost, right? But dependent on what, right? What is this x-axis? I have no label on it. And this is just saying how much does a speeding ticket cost? For what? For walking, for biking, for running, for driving, right? You need to be a little bit more descriptive in your title. And then this guy doesn't have an axes label as well. The other thing I was noticing is that there's a huge break in here that they didn't say y, right? So they've got this 40 spacing between each of these, and then this is supposed to be a 40 spacing as well, and yet it's farther than any of the other spacing. So just make sure that that first one, unless you put a break in the graph, make sure that the spacing is the same throughout. All right, so now we know what makes a good graph. Let's do it. So, before we actually graph ourselves, there's some steps here. First thing I want you to be able to do is interpret a linear graph. So in Physics 50, we will only be analyzing linear graphs, which is great. Okay, so we are going to be looking at linear relationships. An example of a linear relationship is shown below. This is the effect of displacement on a motorboat in still water. Okay, I guess it'd be the effect of time on displacement. So they left out the word the effect of. It's just displacement of a motorboat in still water. So what this is showing is that your displacement is increasing as time increases at a constant rate. We call this a direct linear relationship because it went through the origin, which is 0, 0. We will only be looking at direct linear relationships when we graph. Otherwise, we have to look at what y-intercepts are, and it just becomes a little bit more confusing. So even if you are doing that in Math 50 right now, we don't have to. We can all put it through 0, 0. Because of this, the equation of our line will be y equals mx if you're taking Math 50, or in physics we like to call it y equals kx, where y is your dependent variable, the one that you measure. M is the slope, or in physics we like to call it the constant of variation, k. And then x is your independent variable. So how do we calculate slope? Well, slope is the ratio of the vertical change to the horizontal change. We use the formula rise over run, or change in y over change in x, or y2 minus y1 over x2 minus x1. So now that we know all this information, let's just make this a little bit smaller so we can fit things on one page. What type of relationship is displayed in the graph above? Well, it is a direct linear relationship. Because of that, we can find the slope of the line. How do we find slope? Well, it's rise over run, so I can actually count a rise and see how far I run. Okay, or you could take 2 points. So this is a point 4 and 40. Right? Or I could have taken this point here, 3 and 30, or so on. You could take any point, and I would take this point here, 0, 0, and I would calculate the slope. So the slope is going to be y minus a y. So whether it's 40 minus 0 or 40 minus 30, it doesn't matter. And then x minus an x. So I've got 4 minus 0 or 4 minus 3. Doesn't matter. I'm left with 40 divided by 4, which is 10. So the slope of this line is 10. Question is, what does the slope represent? It's a constant of variation, meaning it's a constant rate of change. What's changing? Well, the slope is a measure of the change of displacement over time. You could put change in time, but we know that time goes on. So the slope is representing your change in displacement over time, or some people might go even further to say that displacement is measured in meters and time is measured in seconds. So it is your meters per second. If anybody knows what those units represent, it's your speed. So a displacement versus time graph, the slope is representing the change in displacement over time, which is your speed of travel. You don't have to know that, but if you do, that's great, because there's 2 more things you'll be asked to do. Number 1, you'll be asked to find the equation of the line using appropriate variables, and then you're going to be asked to describe the relationship in words. So the equation of the line using appropriate variables, it's y equals mx or y equals kx in physics, where the y variable is representing displacement, so we're going to give it a d. The k is my slope, which is 10, and the x is time, which we would give t. So this is an equation of the line using appropriate variables, because this is more helpful than y equals 10x, because I know if they give me a time, I can put it in here. If they give me a displacement, I can put it in here. If they ask me how far did the object go or the motorboat go in 10 hours, I could put in time as 10. The displacement of the boat would be 10 times 10. It's 100, right? Anything along those lines. But I like variables d for displacement and t for time. What is this relationship in words? Well, I'm going to type because my printing is kind of atrocious. The relationship in words, every semester I feel like I write this a little bit differently. I feel like I'm starting to sort of level out, but I would say something along the lines of there is a direct linear relationship between displacement and time at a rate of 10. Now, because we know the units, let's put them in meters per second. So you can use the units from your slope representation in here, or you could say something like there is a direct linear relationship with displacement and time where the change in displacement over time is 10 meters per second. I prefer something simple like that. All right, hopefully that made sense, and because we're now going to do it 2 more times just to make sure you know what we're doing. So here is another graph. This one is the effect of time on the temperature of a water bath. First off, what type of relationship is displayed in this graph? This should get repetitive. It is a direct linear relationship, which means we can find slope. Now, I chose this one as the next level up because this one, you'll notice my dots were on the line, right? Every single point was on the line. So we didn't really have to do a line of best fit. We got to just connect the dots. For this one, this is a graph where a line of best fit has been drawn. So you'll notice there's some points above, there's a couple points below, and in fact, there's no points on the line except for 0, 0. So to find the slope of this line, what you're going to be looking for is a point that you could find where the line passes through. So it's not going to be a data point, it's going to be like a point where the grid lines cross. So for example, my eye went straight to this one. When you have a line of best fit, you do not use data points for the slope. Please, please, please. Instead, you look for a place that your line passes through a nice grid. Like where's another one? There's another one that's really nice. You could use that one. That one's not too bad. It's not as on these other two. That one's not bad too. You could use that one. Okay, but let's use the first one we saw. Now we have to figure out what the scale is. So it took us 1, 2, 3, 4, 5 grid lines to get to 2. So 2 divided by 5 is 0.4. So it means every grid line is worth 0.4. And if you made the graph, you'd know that. So this is 6.4 in my x-axis. And then for my y value, so this is an x value of 6.4, and my y value, oh, look at that. I don't even have to find out. It's 25. So now to find the slope, my slope is going to be my change in y. Now, if you always use the point 0, 0, you could just do y over x, right? Rise over run. So I'm going to do 25 over 6.4, and my slope is going to be 25 divided by 6.4. Comes out to 3.90625. Now, what should we be doing for sig figs? That's a hard one. This isn't my data. You know, if I was reading this, I would say that this is 6.40. I would say that this is 25.0. So I would say that these are each 3 sig figs. So I'm going to answer to 3 sig figs. I'm going to say 3.91. And again, if it was your data, it would be a lot easier to know how many sig figs. I'm just sort of guessing based on my grid lines what I could use as sig figs. What does this slope represent? Well, the slope would be the change in temperature over time. The units would be degrees Celsius per minute. So if I was to write the equation of this line using appropriate variables, again, it's y equals kx or y equals mx. I'm just using the k, I don't know, to be physicsy. I really do love y equals mx. It does not matter. My y variable is temperature, so I'm going to give it a t. My K value is 3.91, and my X value is time. Now I already have a capital T for temperature, so I'm going to use a little t for time. So my equation of my line would be temperature is dependent on time with a constant rate of 3.91. To describe this relationship in words, I'm trying to be very formulaic. There is a direct linear relationship between temperature, I don't need to capitalize that, temperature and time at a rate of 3.91 degrees Celsius per minute. In other words, the temperature of your bath is increasing over time. It's increasing at a rate of 3.91 degrees Celsius every minute. One thing I haven't pointed out until now with this one is that if I zoom in on this graph, what I want you to see is this equation. When we do equations or when we do graphing in a computer, this is a computer generated equation. They are saying that the exact slope of this line is 3.902. We said that it was 3.91. Pretty darn great. It's a margin of error. You know, I looked at this line being through this place perfectly. If we put more grid lines in, maybe we could find a better spot that would give us 3.902. But it's more important to me that you can look at a line of best fit and calculate the slope than just pulling something from a computer. But it's really good to go back and check, which is why I always leave this on here. And so in the end, when you get here, you want to make sure that this equation is close to that equation above, but with more appropriate variables. All right. The last thing we're going to do is draw and interpret graphs, but I think I'm going to pause this video. You could practice interpreting the graph that's in the worksheet, and then you can come back and watch this next video on how to generate a graph.